Hello friends, today I am now going to discuss beta decay selection rule. Beta decay selection rule means suppose in case of nuclear physics, we know that there are various types of decay. That is, one is alpha decay, another is beta decay, another is gamma decay. Okay, there are various types of decay in case of nuclear physics. So among which today we'll discuss beta decay selection rule. That means whether a beta decay is allowed or forbidden. Beta decay transition is allowed or forbidden. Today we'll discuss about this. So let's start discussion. So how can we say that the transition, that beta decay transition is allowed or forbidden? And among allowed, there are various types of allowed transition. That is Fermi transition, Fermi allowed transition, gamma transition. So let's start the discussion. So whenever beta decay occurs, a necessary condition for beta decay occurs is that stable beta decay, that neutron by proton ratio must be less than equals 1.7. So whenever in case of any atoms, in case of nucleus, whenever the neutron by proton ratio is near less than equals 1.7, then that beta decay is stable. And whenever it is greater than 1.7, then that beta decay is unstable. Whatever, that's not our topic of discussion today. So our topic of discussion is whenever beta decay transition occurs. Beta decay transition is occurring. So there are two types of transition. One is allowed transition. Another is forbidden transition. Allowed and forbidden. There are two types of transition. So how can we classify or how can we distinguish between allowed transition and forbidden transition? So let's have a discussion about that. So allowed transition. Allowed transition means whenever small l value is 0, whenever small l value is going to be 0, then what happens? Beta particle emits with neutrino. Beta particle and neutrino emits with L equals 0. In that case, allowed transition happened. So among the allowed transition, there are two types of transition. One is Fermi transition, another is Gamow-Taylor transition. Gamow-Taylor transition. So how can we classify these two types of transition? So Fermi transition means whenever in case of beta decay both electron and neutrino emits with opposite spin. Whenever in case of beta decay, when electron and neutrino emits with opposite spin means what? Opposite spin means delta S equals 0 and spin value is what? Delta is what? 0. Means whenever electron and neutrino is emitting, that means if electron spin is plus half, then neutrino spin should be minus half. That means what? Delta is equals 0. And for allowed transition, what we have studied? For allowed transition, we have studied that small l equals 0. That means what? Delta J equals 0. That means no. And another thing is, in this case, for allowed transition, no parity changed. And here 0 to 0 transition will be allowed. So what we can summarize in case of Fermi transition? In case of Fermi transition, so we can summarize that whenever allowed transition occurs, that means electron emits with neutrino So these types of things are going to be happened. One is delta S equals 0, another is delta J equals 0, delta S equals 0, and we know that L equals 0. Another is delta J equals 0, and no parity change, no parity change, and fifth point is 0 to 0 transition allowed. So this is allowed Fermi transition. Another types of transition is allowed transition. Another type of transition is Gamow-Taylor transition. Gamow-Taylor transition. Gamow-Taylor transition is what? So let us discuss Gamow-Taylor transition. So whenever we are going to discuss Gamow-Taylor transition or GT transition, you can say, then electron spin and neutrino spin both are parallel spin. Parallel spin means what? If it is half plus half, it will be plus half. That means what? That means delta S equals 1. And delta S equals 1 means what? For allowed transition is what? For allowed transition L equals 0. So in this case, what will be happen? In this case, delta J should be 0 plus minus 1. So for Fermi transition, delta S equals 1, delta J equals 0 plus minus 1, and delta S equals 1. And in this case, no parity change. No parity change will be occurring. But the most important thing is here 0 to 0 transition not allowed. So in case of Fermi transition, what we can summarize, in case of Gamow-Taylor transition, we can summarize that here delta S equals 1, here delta J equals 0 plus minus 1, no parity change, and last but not the least, that is 0 to 0 transition not possible here, not allowed. So let's take an example. What kind of example we can take? Suppose a nucleus whose J value is half and parity is plus half. Okay. Another nucleus whose J value is half, parity is plus half. So another product is electron plus neutrino. Okay. So in this case, what we can say? In this case, we can see it is J value. Here it is Ji. Here it is Jf. So delta J value is what? Delta J is 0. Delta J is 0. That means what? Delta J is 0. That means it could be what? It could be Fermi as well as it could be Gamow-Taylor transition also. Yeah. Because here delta J is 0 and delta J is 0 is possible both Fermi and Gamow-Taylor transition. Another thing, suppose let us take an example where J is 0 plus and here transition is happening 0 plus electron neutrino. So here what kind of transition it is? Here Ji is 0 and Jf is 0. So delta J will be 0. But how can we say that it is Fermi or Gamow-Taylor? Because in case of Fermi also we have studied that delta J should be 0. In case of Gamow-Taylor we have studied that delta J may be 0. But in case of Fermi, 0 to 0 is allowed. 0 to 0 transition, J equals 0 value to J equals 0 value transition is allowed. So we can say that it is Fermi transition. In this way, we can say that allowed transition allowed transition are such that we can, so let us summarize the allowed transition. Allowed transition are such that where there are two types of allowed beta decay allowed transition. One is Fermi transition, another is what? Another is Gamow-Taylor transition. So in case of Fermi transition, what we have seen? In case of Fermi transition, we have seen that delta is 0, delta J is 0, L is 0. Allowed transition for L is 0. In case of Gamow-Taylor transition, what we have seen? In case of Gamow-Taylor transition, we have seen that in this case, delta is equals 1. That means electron and electron neutrino parallel spin. And here what we have seen, another thing is that in case of Gamow-Taylor transition, we have seen that in this case electron and neutrino are parallel spin. So delta S equals 1, delta S equals 1 in this case. So delta J equals 0 and plus minus 1. And both case parity will not be changed. And but last but not the least, in this case J equals 0 to 0 value is allowed. But in this case J equals 0 to 0 value is not allowed. So this is allowed transition. In our next session, in our next video, we'll discuss about the forbidden transition. In our next video, we'll discuss the beta decay forbidden transition. So for the time being, thank you. In our next video, we'll discuss forbidden transition of beta decay. Bye.